We can take the previous result for a single particle, which said that the change in momentum is equal to the impulse, and generalize it to state what's known as the impulse momentum theorem. And that theorem says that if you have a system of two masses, for example m1 and m2, could be any number, but for simplicity let's state it in terms of two masses, then the total initial momentum plus the impulse, and that's going to be the total force acting on the system, is equal to the total final momentum. And so to write that out, m1 v1 sub I plus m2 v2 sub I plus the force, external force on 1 plus the external force on 2 times delta t. Delta t represents the time interval over which this is being considered, is equal to the final momentum, which is for the system, which is m1 v1f plus m2 v2f. So to take an example of this, let's consider two masses m1 and m2. m1 has a velocity to the right of v1I, and m2 is initially at rest. And let's say m1 hits m2 and they stick together. This is known as a completely inelastic collision. And the masses in combo have a velocity to the right of v sub f. So let's say that m1 is 1 kg, m2 is 1 kg. The initial velocity of v1 is 1 meter per second, and the time interval of consideration is 0.1 second. That is to say, we want to consider the time interval 0.1 second after the collision. And let's say that mu is equal to 0.2. So this is not a frictionless situation. There is an external force acting on m1 and m2, and we're considering m1 and m2 to be the system. So to use the generalized impulse momentum theorem, we first write down the initial momentum, which is 1 kilogram meter per second. And then we write down the impulse acting on the system. Well, this is going to be the frictional force, which is acting in the negative x direction. And it's going to be the normal force, which in this case is just m1 plus m2 times g times mu. And that turns out to be negative 6 newtons. And the impulse then is the force on the system times delta t, which is negative 6 newtons times 0.1 seconds. There should be a seconds there, minus 0.6 newton seconds. And that means that the total final momentum is equal to the total initial momentum plus the impulse. So the total final momentum is then equal to 1 kilogram meters per second minus the impulse, which we just computed to be minus 0.6 Newton seconds. I think these units are messed up. Newton times seconds is what I meant. So 1 minus 0.6 is 0.4 kilogram meters per second. Remember, the Newton seconds are the same units as kilogram meters per second. And we can then say that the final momentum, which is 3 kilograms times v sub f, is 0.4 kilogram meters per second in the x direction. And we can simply solve for v sub f by dividing both sides by 3 kilograms. And what we conclude from the impulse momentum theorem is that this final velocity of these two masses sticking together 0.1 seconds after the collision is 0.13 meters per second x hat. In other words, 0.13 meters per second in the positive x direction.